Okay, we continue with week 3 concepts.
Hello, sir. Hello, sir.
Hello.
Say, is this week's week 3 lecture for Monday is available on Moodle?
Yes, this is week 3.
The Monday's lecture is available.
Yes, it's on. Let me. I will show you. Can you see my desktop?
Yes, yes.
This
Yes.
is week 1, week 2, and on week 3 lecture notes. This is the lecture notes for this week. For all of the weeks, I have uploaded already. I uploaded week. This is lecture notes for week 4, week 5, and so on. Okay.
Okay. Say, what about the recording for Monday?
The Monday I will upload the videos on Friday each week. I will upload the videos for Monday, Wednesday, and Thursday. On Friday, I will upload all of them at the same once a time on Friday.
Okay, sir.
Okay, so let me start. Okay, we continue with the logarithmic decrement. In logarithmic decrement, I explained that how we can extract the relation between the amplitudes in two consecutive cycles, for example, for x1 and x2, and then we can substitute into the relation for the response. Instead of t, we can substitute t is equal to t1, and for x2 we substitute t is equal to t sub 2, and then we find the ratio of x1 to x2 by simplifying this equation, because we know that t2 is equal to t1 plus the period, and the period is equal to 2 pi divided by omega d. This is the definition for the period. And omega d is the frequency of the damped system, and it's equal to the natural frequency, which is omega n times by square root of 1 minus psi squared, and psi is the damping ratio. So we know all of this information. We can substitute and simplify, and we can convert the cosine form into the exponential form and simplify. And finally, we will have this term, which is the ratio of x1 to x2, the ratio of the response into two consecutive times. And then we can find the ln of this term, which is called the logarithmic decrement, delta. So this is the delta, and then it's equal to psi omega and tau d, and we can substitute instead of tau d, we can substitute for this term, which is 2 pi divided by omega d, and psi times by omega n, which is equal to c divided by 2m, and then you can simplify this equation. And finally, this is the relation between delta and damping ratio. Here you can see that delta is a function of damping ratio, and then you can extract again another equation, which is the damping ratio as a function of delta. In the real world, most of the time, we can obtain delta, as you will see in some examples I will solve today for you. You will see that most of the time we can obtain delta. And by using this delta, we can obtain the damping ratio using this equation. So the practical application of the delta and logarithmic decrement, in fact, in the real problems, when you deal with a system that you don't have any information about the damping in your system, you can use this equation. I mean, you can excite your system. You can, for example, subject your system under an initial condition and get the response, for example, the xt or x dot or acceleration, and using the graph of your response, you can obtain delta. And finally, by using this equation, you can obtain the damping ratio in your system. So this is the main application of the logarithmic decrement, and we can obtain the damping characteristic in your system, in your unknown system. And another point, you can obtain the delta, the damping, the logarithmic decrement for different cycles. For example, you have the response at the cycles, in the first cycles, for example, x1, and also you have the response for another time, t sub m plus 1, which is equal to t1 plus m times by the period, and m is the number of the cycles between the first t1 cycle and t sub m plus 1 cycle. So you can use this equation to obtain delta. And again, as I told you, t sub m plus 1 is equal to t1 plus m times by the period. So you can obtain delta or the logarithmic decrement between any different cycles. Here in this response, for example, if you have x1 and, for example, x3, if we call it, for example, x3, by using this term x1 and x3, again, you can obtain delta from the data in x3 and x1 cycles, or here, for example, x4. So any cycles, when you have the information for any of these cycles, you can obtain the delta using these informations and this equation. And also you can use the graph for the velocity or acceleration to obtain delta. Again, the same equation. I mean, instead of x, you can use the x dot or x double dot. Sometimes you use some graphs that you have the information of the velocity and acceleration. And in fact, actually in the real world, usually you have the acceleration. Here you can see this is the x double dot. Most of the time in the real world, because we use the accelerometers, and by using the accelerometer, we can extract the graph for the acceleration. You will see in the week 13 or week 14 that I will explain you how to use the accelerometers and how to monitor the vibration of a real machine. You will see that in the practical applications, we usually have the graph of the acceleration versus time. And by using that graph, you can obtain the delta, and you can extract the damping in your system, okay, by using this information. So in the real world, most of the time we have the acceleration, and from the acceleration, we can obtain the natural frequency, and also we can obtain the logarithmic decrement, which cause to obtain the damping ratio. Any questions so far? Is it clear?
Yes, sir.
Okay. The next concept that here we discuss is the energy dissipated in a viscous damping system. If we extract the rate of change of energy with time for a system which has only one damper, it's equal to the force times by the velocity. For a system with one damper, the force is equal to c times by x dot, and the velocity is x dot. So we will have cx dot squared, and also we have one negative sign here because the force is in the negative direction of the motion, so we can assume one negative sign for the force, and the velocity is x dot. So this is the force in dE to dt, or the derivative of the energy with respect to time, or the rate of change of energy with respect to time, and it's equal to minus cx dot squared. And this is for a system with one damper. But when we have the spring in our system, this force F is equal to minus cx dot plus kx, and this time again we have one additional term, which is the force due to the spring, and it's equal to k times by x. Again we have one negative sign because this force is in opposite direction of the motion, and the velocity is again x dot. So we can use this term to obtain the total energy for your system, or by considering the xt as a simple harmonic motion, which usually in the vibrating system we have this term, we have a harmonic motion. And if you substitute for your the velocity in your equation and for your displacement, you can obtain the energy for a cycle, which is equal to pi times by c times by omega d times by x squared, which this uppercase x in fact is the amplitude of your response. Omega d is the frequency of the damped system. C is the damping constant in your system. And you can see for a constant value, or for a given data for your system, when you have the damping constant, and also when you have the amplitude of the response, the energy in your system is still it's not a constant value, and it's a function of the frequency of the damped system. So we prefer to find another form for the energy in your system, for the energy dissipated in a cycle, which is it should be a constant function, or at least it should be a function of the characteristic of your system, such as the damping ratio. So for this purpose, we can find the total energy in the system, and you know that the total energy in your system is equal to the maximum energy, the maximum kinetic energy here, or the maximum potential energy. And from the Rayleigh's method, you know how to obtain this by considering the maximum value for the sine or cosine harmonics. And finally, by finding the ratio of the energy dissipated in a cycle to the total energy of the system, we can substitute and simplify this equation. And by simplifying, you can obtain that the ratio of delta E, or the energy dissipated in each cycle, to the total energy of the system is equal to 2 times by the logarithmic decrement. And if you substitute the delta, or the logarithmic decrement, as a function of the damping ratio, you can obtain that this ratio is equal to, of course, approximately is equal to 4 times by pi times by psi, when psi is very small for an underdamped system. So this is this term is constant, as you can see, and this is called the specific damping capacity for your system. So the application of this equation is in fact in the next chapter, when we want to find an equivalent damping coefficient for a system with column damping, and we want to model a system with column damping as a system with viscous damping. And the purpose is because most of the time when you deal with a system with column damping, you cannot find a linear response for your system, because the equation of motion for a system with column damping is a nonlinear equation. You will see in the next chapter. And we prefer to have a linear equation of motion to solve. So for this purpose, we need to obtain an equivalent damping constant for the system and an equivalent damping ratio for the system. By using this equation and this formula, we can use to obtain an equivalent viscous damped system for example, a column damped system, to obtain a linear equation of motion. So for now, you only can understand that how we can find an approximation for the energy dissipated during a complete cycle in a system with viscous damping, and it's equal to 4 times by pi times by psi. For a torsional system, if you extract the equation of motion, it will be exactly the same in terms of the mathematical point of view. It's exactly the same as a translational system. Instead of the mass, we will have the mass moment of inertia, and this time we will have the damping constant. This time, instead of a linear damping constant, we will have a torsional damping constant that we show with C sub t. And Kt, as I explained in previous section, is the spring constant for a torsional spring. So the solution for this system is exactly the same. I mean, we will have a second order ODE. You need to obtain the characteristic equation, find the roots of the characteristic equations, alpha 1 and alpha 2. You need to obtain the natural frequency damping ratio, and all of the characteristics are the same. Here you can see as the linear system and translational system. So easily you can obtain the response by using the previous method and previous formula, and the response is the same. But this time, instead of x, we will have theta. Any questions so far? Is everything clear? Okay. Okay, we continue with one example. Here we have an under-damped shock absorber is to be designed for a motorcycle of mass 200 kilogram. When the shock absorber is subjected to an initial vertical velocity due to a road bump, the resulting displacement time curve is to be as indicated below. Find the necessary stiffness and damping constants of the shock absorber if the damped period of vibration is to be 2 seconds and the amplitude x1 is to be reduced to 1/4 in 1/2 cycle. It means that x1 x sub 1.5, this amplitude is equal to x1 divided by 4, this amplitude divided by 4. So we can use this information. In fact, we want to design an vibration absorber for this system. The mass of the system is 200 kilogram. We know that the period must be 2 seconds. So we have the period, it's equal to 2 seconds. Easily we can obtain the natural frequency from this period, omega n. And also we can obtain the delta by using the information of the amplitudes, the relation between the consecutive amplitudes in x sub 1.5 and x sub 1, because the same relation is between x sub 2 and x sub 1.5. So we can find the relation between x2 and x1. Okay, so as I told you, we have the relation between x sub 1.5 and x sub 1. So x sub 2 is equal to x sub 1.5 divided by 4. And instead of x sub 1.5 we can substitute from this term, which is x1 divided by 4. So finally we can conclude that x sub 1 is equal to 16 times by x sub 2. And if you substitute into the equation for the logarithmic decrement, you can obtain that delta is equal to ln of 16, which is equal to 2.77. And you can substitute for the damping ratio into the equation as a function of delta. We have delta, which is 2.7. You can substitute. And finally, the Kasai or damping ratio, which is equal to 0.4. And as you can see, it's less than 1 for an underdamped system. And here from the response, you can see that this is an underdamped system. The next step, we need to obtain the frequency for the system. And also you need to obtain the stiffness and damping constant. The period for this system is 2, so the frequency of the vibration is equal to 2 pi divided by the period, which is equal to pi. This is the frequency of the system. And also we know that the frequency of a damped system is equal to the natural frequency multiplied by square root of 1 minus Kasai squared. Kasai is obtained here is 0.4, and omega d is obtained here is pi. So easily the natural frequency of the system will be obtained 3.45. As you can see, the frequency of the undamped system is more than the frequency of the damped system. So, and this is a trivial conclusion. The next step, we need to obtain the critical damping and also the damping coefficient for your system. You know that the critical damping is equal to 2 times by the mass times by omega n. And also we know that it's equal to C divided by damping ratio. So from here, we can conclude that C is equal to Kasai times by 2 times by M times by omega n. M is given data, omega n is calculated here, 3.45. And damping ratio, which is obtained here, 0.4. So we can substitute and simply, easily we can, by simplifying this term, you can obtain that the damping constant must be 552.36 Newton meter per second. This is the coefficient for the damping. So we need a damper with this coefficient if we want to have a response like this. And the next step, you can find the K by using the relation between the stiffness and the natural frequency. You know that the natural frequency is equal to a square root of K divided by M. So K is equal to M times by omega n squared. Again, M is the given data and omega n is the natural frequency of the system. And easily you can obtain that the stiffness, the required stiffness for this system is about 2.4 kilonewton per meter. So to have a response like this for your system, if you want to design an vibration observer, you need to use a spring with the stiffness of 2.4 or 2380 Newton per meter. And also you need a damper with the stiffness of 552.3 Newton meter per second. So this is the characteristic for the system, required system for this response. Any question? Is it clear? You can see the application of delta, the logarithmic decrement here. I mean, we have the response. I mean, for example, in your system, you have an ideal response and you want to achieve to this ideal response. So according to this response, you can design your vibrating system and you can obtain the stiffness, the damping constant, and sometimes even you can obtain the mass in your system. I mean, you can add some, for example, additional mass to control your system. Is it clear? Any question from this example?
All good, sir.
Okay. Okay, here we have another example. In this example, we have one slender rod has a mass of 31 kilogram and a length of 2.6 meter. A 50 Newton force is statically applied to the bar at P at this point. This point is P. And an oscilloscope provides the acceleration data shown in below. Use the data to find the spring constant K and the damping coefficient C. So we have this system and we don't have any information about the damping and about the stiffness in this system. I mean, these are the unknown, but we have the acceleration graph for this system, which is subjected to this force 50 Newton. So we need to obtain the equation of motion for this system by in terms of two unknowns C and K, and then we can use this graph to obtain delta, and consequently we can extract the damping ratio for the system, and also we can obtain the natural frequency in this graph and the period. So we can obtain C and K from the equation of motion and also from this graph. But here there is an important point that when you want to extract the equation of motion, the equation of motion is not equal to mx double dot plus cx dot plus kx, and m it's not 31 kilogram because this is a rigid body. It has a rotational motion. So similar to the dynamic problems, you need to extract the equation of motion by writing the Newton's second law. Here, the best option is writing the moment equation about this point. If we call it, for example, point O, if you write the moment equation about point O, you can easily extract the governing equation for this system and find the equivalent mass, equivalent stiffness, and equivalent damping coefficient. So for this purpose, we write, as I told you, the moment equation. And this is a one degree of freedom system, a single degree of freedom system, because here, if you assume that xt is the degree of freedom, it's a function of theta, and theta is the rotation about the equilibrium position. Okay, so if we call it theta, xt is equal to 1.95, this term, times by theta, and 1.95 is the length of this arm. Okay, the distance between point P and point O. So by using xt, we try to extract the equation of motion. We can write the moment equation according to the Newton's second law. We have the moment equation about point O. As I told you, this is point O. This is point O, and the rotation point. It must be equal to IO times by alpha, which IO is the mass moment of inertia about point O, and alpha is the angular acceleration, or theta double dot. So it's very important that this is IO, it's not IG. I mean, it's not the mass moment of inertia about the mass center. This is the mass moment of inertia about the fixed point O. From dynamic, you know that from this equation, you can easily extract the equation of motion. So if you plot the free body diagram for this system, of course, there is a different for this system and in vibration and dynamic. If you solve this equation, this system for dynamics, you must consider the weight of this bar. But here you can see we neglect the weight, and also we neglect this 50 Newton force, as I told you, because first of all, the weight will create some initial deflection in the spring. So we neglect the weight, and also we neglect the initial deflection in the springs, because these two terms will cancel out each other in the equation of motion. But this 50 Newton force, in fact, only creates some initial condition, so it's not considered in the equation of motion. Okay, so the moment equation about point O is only due to the force of the spring and the force due to this damper. the force due to a spring is equal to K times by X multiplied by its arm, which its arm is equal to 1.95, because you're calculating the moment about this point O, and this point O, the distance between force of the spring and point O is equal to 1.95. And for the damper, that arm is equal to 0.65, as you can see here. And the force is equal to C times by this length, again 0.65 times by theta, which theta is equal to X divided by, from this equation, you can conclude that theta is equal to X divided by 1.95. So this is theta, and here we know that the force in this damper is equal to C times by the displacement of this point. The displacement of this point is equal to 0.65 times by theta, and as I told you, theta will be substituted from here. So we will have, instead of the velocity of this point, we will have 0.65 times by theta dot, and theta dot can be obtained from here. I mean, theta is equal to X1 divided by 1.95. So theta dot is equal to X dot divided by 1.95, and we can substitute here. And finally, the summation of the moment about point O will be obtained from these two terms. And IO, which is the mass moment of inertia about point O, again from dynamics, you know that the mass moment of inertia about a fixed point O is equal to the mass moment of inertia about the mass center plus m times by d squared, which m is the mass of the system and d is the distance between the mass center and point O. Here you know that the mass center of this bar is exactly at the center, and the distance between the mass center, which we call it, for example, G, and point O is this length, and it's equal to 0.65. If you want to calculate this length, if we call it, for example, D, you know that D is the position of the mass center minus the position of point O with respect to the end of the bar. So the total length, or the position of the point G, is equal to 1.95 plus 0.65 divided by 2. I mean 1.95 plus 0.65 divided by 2. This is the half length of the bar, and then we should minus 0.65. It will be the D. So this is the half length. If we call it L divided by 2, this is the half length of the bar, and then this term minus 0.65 is equal to D. So we can substitute and find the mass moment of inertia about the mass center. And as I told you, alpha is equal to theta double dot. And theta double dot can be substituted again from this term. It's equal to X double dot divided by 1.95. So we can substitute all of these terms into the equation and extract the equation of motion by simplifying these terms as a function of X. So here you can see this is the equation of motion. This is the equation of motion as a function of X. And now you can see this term is the omega n squared. This term is 2 times by C times by psi times by omega n. So from these two terms, we can obtain the damping coefficient and the stiffness in this system. So these are the equivalent mass and equivalent stiffness, and also the equivalent damping coefficient. So we need to obtain first the natural frequency by using this graph and also the damping ratio. So next step, we need to obtain the damping ratio and the natural frequency for this system. Here you can see from this data, from this graph, we can obtain delta, which is ln of as I told you, instead of x, we can substitute the acceleration because this graph is for the acceleration. The acceleration at point t with divided by the acceleration at point 1, because it's clear that the period of this system is 0.1. So x1 is equal to x at this point, and x2 is equal to x at this point. Okay, so we can substitute ln of 3 divided by 2, and it's equal to 0.4. This is the delta, and from delta you can obtain the damping ratio from the equation, and it's equal to 0.064. This is the damping ratio, and again, as it was observed from the graph, this is an underdamped system. The damping, the frequency of the damped system is 2 pi divided by the period. Period, as I told you, is equal to 0.1. Here it's clear that this is the period of the system. 2 pi divided by period is equal to this term, which is the frequency of the damped system. And by using the omega d and the damping ratio, we can obtain the natural frequency of the system, and it's equal to 62.96. As you can see, the value of the omega n is very close to the omega d, or the natural frequency of the undamped system is very close to the natural frequency of the damped system, and this is due to the small value of the damping ratio, because the damping ratio is very small. So we can conclude that omega n is very close to omega d. The next step, we must obtain c and k. For this purpose, we use the equation of motion. As I told you, omega n squared is the coefficient of x, and also we can use the coefficient of x dot to obtain the c, or the coefficient of damping, or the damper. So by using this equation, we can obtain k and c, which these are the required stiffness, 32.3 kilonewton per meter, and the coefficient of damping must be equal to 583.9 Newton second per meter. So these are the required value for a spring and for the damper. Is it clear? Any question from this part? If you don't have any question, we can wrap up this session. Okay. Thank you for your attention, and we continue tomorrow by the next concepts, and also tomorrow we will have the tutorial sessions as well. Okay, thank you and have a good day. Bye.